I'm going to recap 1-2 minutes about Ohm's law, how it's applied in physio. Then we're going to talk about the relationship between pressure, flow, and resistance, and how does compliance of a vessel affects the flow. Then we're going to talk about what are the pressures in cardiovascular system, what are the importance of each of it, and how do they relate to each other. Then we move on to fluid dynamics, where the equations comes into play. How the flow, volume versus flow versus velocity is important, and what do they mean by laminar versus turbulent flow, and how do they, again, Poiseuille equation and Reynolds number is involved in determining this laminar versus turbulent flow. And finally, we talk about LaPlace flow, which is equally related to all these fluid dynamics as well. Okay. Okay, again, core SP, Ohm's law is an electrical equation which has been extrapolated in use in a lot of physiological situations, especially cardiovascular and respiratory system. Simply, it stands for V equal to IR. V is the voltage, I is the current, R is the resistance. As we extrapolate into a cardiovascular system, the I will be the flow. You rearrange it. V equal to IR will be I equal to V over R. I will be flow. V is the pressure. The potential voltage difference will be the pressure difference, pressure gradient, and R will be the resistance. So as we know, as for a flow in the y-axis and pressure in the right axis, x-axis, as the resistance is lower, with any increase in pressure, the flow will increase. Logical. Okay. If there is increase in resistance, you have to apply more pressure to get the same flow. So that's the difference. Okay. So as in flow, in cardiovascular system will be cardiac output, and for pressure gradient will be MAP, and for resistance will be a vascular resistance, which will be a systemic vascular resistance or total peripheral resistance. So V equal to IR will be, V is the potential difference in voltage, will be a potential pressure gradient, which is cardiac output times systemic vascular resistance. We rearrange it to get the flow, which is the I, which is cardiac output equivalent to pressure differences, which is mean arterial pressure divided by your systemic vascular resistance. So again, we come back to this equation. So MAP is equivalent to diastolic blood pressure plus 1/3 pulse pressure. It's all the same. I'm not going to go into. So we came back to this main equation where MAP is equivalent to cardiac output times systemic vascular resistance. So your pressure differences determines your flow based on your systemic vascular resistance. Everyone else, please mute. Okay, so we come back to this equation, and a lot of our equations gonna come into play and gonna relate to this. Okay, pressure. We go into basic. Before we're going to talk about the flow dynamics and everything, we go into basic. What is pressure? Pressure is force over area. Okay. Amount of pressure applied over an area gonna create a pressure. Okay. This is the area, the force being applied onto this surface area gonna cause a liberation of a pressure. That is pressure. Okay. So what is blood pressure? Blood pressure will be the force exerted by blood on the vessel wall. So this is the blood. Blood is exerting their pressure, this force over this area of the blood vessel that gonna cause the pressure. So if you look at it, this is the blood vessels. In the blood vessels, this is the area of the blood vessel, which is the diameter of the blood vessels, and blood is flowing through the blood vessels, and the blood flow gonna exert the pressure on both sides towards the circumference of the on the walls of the vessel wall. So this force over the area of the vessel is the one that causing pressure. So force over a certain area is going to cause pressure. Force over an area is the pressure that being liberated by the blood. So that is called blood pressure. So we can easily say, if we just look at it here, this is the normal. If you have an arterial line, this is the normal blood pressure where you have your systolic blood pressure, diastolic blood pressure, and under this is MAP. So we don't have to look into this waveform now. I'll come into it later. But what I want to show you is, if you have a patient with arteriosclerosis, it means the patient's vessel wall is hardened. So this is a normal vessel wall. If the patient with arteriosclerosis, the vessel wall is thickened, hardened. So in this patient, we need more force. The blood will have to apply more force over this area. Okay, the force that applied by the blood vessel will increase over the area. That's why patient with atherosclerosis, peripheral vascular disease, they will have a higher blood pressure. The systemic blood pressure, systolic blood pressure will be higher because their vessels are stiff and non-compliant. So the blood flowing through it will exert more force on the vessel wall. That is causing the increase in blood pressure. Okay. This is an example. We'll come to more examples later. So blood flow relation to pressure is, it follows the pressure gradient. Blood flow from high pressure to low pressure areas. So your arterial system and venous system, your system have low pressure compared to your arterial system. So your blood will flow from the, let's say from the left ventricle into the major arteries, going into arterioles and your capillaries, then into venules, then went to veins and major veins of vena cava and everything back to the heart. That is the return of circulation. So we're gonna get into the waveform of it. We can see initially the flow is pulsatile because the blood is being ejected from the left ventricle into the aorta with a larger pressure. So it's pulsatile. As the blood flows through the blood vessel into the system in a long travel, it's gonna undergo friction which is produced by the vessels, and it's gonna lose the kinetic energy and mechanical energy, and the pressure will drop further and further and further. So that is why from high pressure to low pressure, the blood system gonna come down. So if you can see from your aorta to your vena cava, the pressure differences is major. That's why the pressure is pushing your blood forward from your arterial system back to your heart as a venous return. And we compare systemic circulation and our pulmonary circulation as well. There'll be a difference in pressure from your right heart to your pulmonary arteries again. So this is your right heart. After the vena cava, the blood will go into right atrium and right ventricle. Then the pressure differences from the right side of the heart to the left side of the heart is the one that pushing your blood towards your pulmonary circulation. So we can see the blood flow depends on your MAP, not systolic blood pressure, because if it depends on your systolic blood pressure, it won't go from high blood pressure to low, because your systolic blood pressure will be higher here. Then as it goes down, it will fall and fall and fall. So if it's going to follow a systolic blood pressure, the blood is not flowing from higher to low blood pressure areas. A simple example, you measure your blood pressure in your arms versus your legs, but your blood pressure in your arms is higher compared to the legs. Okay, sorry, the systolic blood pressure in the legs is higher compared to the arm, but the blood still from your upper body to lower body because of your gravity and also other effects. I'll come back to you. So the important determining pressure that maintain the blood flow is mean arterial pressure, not the systolic blood pressure. We will do a calculation soon. So next, before we go into other pressure, we're going to talk about compliance. So the compliance is, what we mean by compliance is change in volume over a change in pressure. Means which any change in pressure gradient, how much of the pressure is changed, that determines the compliance of your vessel system. Easy. If the vessel is compliant, it means it has capacitance or it can distance to accommodate more volume. That is the idea of your compliance. So if the vessel is compliant, you give an increase in pressure, it's gonna distend to accommodate more volume. So again, we go back to this. Change compliance equivalent to change in volume over change in pressure. Increase in pressure gonna cause increase in volume, means that will cause increase in your compliance. Let's say increase in pressure, but there's not much increase in volume, that is reduction in compliance, means the vessel is not compliant. Simple example, a normal artery versus a person who have atherosclerosis. The atherosclerosis person, the arteries are stiff, they are not compliant, they cannot accommodate. That's why when there is increase in pressure, the flow according into the vessel is not able to accommodate. They are low compliant. So when there is increase in volume, the pressure have to increase severely to maintain the flow. That's why they have systemic hypertension. So it's based on whether it's a lung. We go back to this. We go back to this. Stiff and non-compliant. When it is stiff and non-compliant, the pressure increase must be very high to maintain the same flow. So that is how the compliance come into play. That also mean important where how does the blood flow from arteries to venous system, because arteries have higher compliance, so they don't have to increase the pressure so much to maintain the flow. So the arterial system have a higher pressure compared to venous pressure, when venous system. That's why the blood is flowing from higher pressure system to the lower pressure system. So venous are high capacitance or high compliance vessel, which only need lower pressure, but they can accommodate more volume. Compared to arteries, even though here the example is atherosclerosis, even normal arteries are low compliance but higher pressure system. Okay, this is the importance of this to maintain the flow. So we go look, and if you plot a graph volume versus pressure, this is for compliance graph. For compliance, volume is always on the y-axis, pressure is on the x-axis. So you can see veins are high compliance vessel. Even a small change in pressure will increase very large changes in volume. They are high compliant. Arteries, whereas they are low compliance system. More increase in pressure is needed to maintain a certain volume. Compared to even ardent arteries or older people and everything, is even more higher pressure is needed to maintain a certain volume. That's why you can see there, according to the age, as the age goes by, you can see the increase in pressure because their vessel compliance comes down. So to maintain the volume, they have to increase the pressure to maintain the volume. So another small things I want to mention is, we always heard the word compliance, but in some books, especially when you talk about cerebral blood flow, elastance, and we talk about RS system, when you talk about alveoli and everything, you will hear a term called elastance. So what is elastance? Elastance is just the inverse of your compliance. If you look at compliance, volume over pressure, but you inverse it, pressure over volume is elastance. Compliance is a tendency to stretch, distensibility, the capability of a vessel or alveoli or whatever cylindrical hollow system can distend to accommodate more volume. Whereas elastance is tendency to recoil. How much they can, once they have distended, how much they can recoil back, because the recoil is also important. As for the heart, for filling, for the contraction, and also the relaxation part. For you to have a proper systole, to increase the maintain cardiac output, you have to have a proper compliance. The heart must be adequately filled during the venous return. Should be able to stretch to accommodate the venous return. And then after the systole, it should able to recoil back. It cannot maintain a stretch again. So otherwise the venous return cannot come back. That will increase in pressure. If it's a low elastance, the pressure will increase. Okay. So that is the inverse ratio. It's very important in cardiac and also cerebral blood flow. If you read the intracranial elastance graph, that shows your ICP increases and everything. Okay. So tendency to recoil is just the inverse of your tendency to stretch. So it's a reciprocal of this. We will see this in when we talk about RS equations and everything. Okay. And we also, when we go into the next few topics, we talk about cardiac cycle, systolic and diastolic in detail. So next we come to the pressures in the cardiovascular system. Some important things we need to know the day-to-day use is systolic blood pressure, diastolic blood pressure, pulse pressure, and mean arterial pressure. What are the differences? What do they actually mean? First, systolic blood pressure. As the name suggests, systolic, it's a force exerted by the blood on vessel walls upon systolic contractile phase of cardiac cycle. Okay, your cardiac cycle has systolic phase and diastolic phase. A part it contract, a part it relax. A part it ejects the blood out of the heart, a part that it receive and fill up the heart. Okay, that is systolic phase is the contractile phase of the cardiac cycle. So the blood that being ejected from the heart goes into aorta and your arterial system. They exert a force on the blood vessel wall. That is the pressure that being recorded. Okay, so that is, it is the pressure against which blood has to be ejected from the heart. In other words, we are saying the vessel we have to push against this. That's why we call it systemic vascular resistance or afterload, in other words. Okay. So if you see, the systolic blood pressure varies in a different arterial system. The more distal the arterial system is, an increase in systolic blood pressure will be seen. Okay, because nearer to the heart, more force. The blood is ejected with a bigger force, but the vessel walls are much bigger. If you talk about aorta and you talk about your femoral arteries and everything, they are much bigger. So the area is bigger. So we go back to our previous equation. Pressure is equivalent to force over area. The force is bigger, but the area also larger. So that's why the systolic blood pressure is not so high compared to distal arteries, where in distal artery, the force is somehow maintained because of the pulsatility of our nature and also something called Wien-Kessel effect. I'm not going into detail about Wien-Kessel effect. You all can read about it. So the Wien-Kessel effect actually maintain the pulsatility of a blood flow and it maintain the force. But as we go distal and distal, our blood vessel gets smaller and smaller. So the area becomes significantly lesser. Pressure is equivalent to force over area. Force is somehow maintained, but the area becomes smaller and smaller. So what happened to the pressure? Pressure increases. So systolic blood pressure is high. That is the reason your systolic blood pressure is high when you go distal and distal compared to your upper body and lower body if you measure your blood pressure as well. Diastolic is force exerted by blood vessel wall upon diastolic during relaxation phase of cardiac cycle. It is the pressure caused by the recoil of arteries during heart filling. Okay, because during the filling of the heart, you have to push back all the blood. Okay, from the arterial to the venous system and to the venous return into the IVC and IVC into the right heart. So this is the pressure that exerted on the vessel wall during the relaxation phase of the cardiac cycle, because recoil of the vessel is important to push the blood forward. Okay, it is a continuous cycle, systole diastole. Same goes to the vessel needs to constrict and then they have to recoil, constrict and recoil. It's like a peristaltic movement of the gut as well. So it is needed to push the blood forward. Then we go to pulse pressure. Pulse pressure is merely a difference between systolic and diastolic. That is the pulsatile nature. The difference between this systolic and diastolic is the pulsatility for blood flow from high pressure to low pressure system. So difference between systolic blood pressure versus diastolic blood pressure, the force that heart generate each time it contracts. It means during each cardiac cycle, systolic and diastolic is comprise one cardiac cycle. Okay, one cardiac cycle, systolic phase and diastolic phase. During these two phases, there is a difference between the pressure. That pressure is the pulse pressure. Okay, so again, as I said, we come to a system. If you draw a curve between pressure and the system, you have your waveform, your arterial waveform like this. Your upstroke at the peak will be your systole, your downstroke and your lowest will be your diastole. Okay, and then the midpoint of this, if you draw a midpoint here like this, that will be your MAP, and the difference between your peak and the lowest point is your pulse pressure. Okay, again, if you look at it, so this is the midline. It's the average of systolic and diastolic will be MAP, but we interested here is the pulse pressure. Okay, the importance is we look at it, as I mentioned, as an example. You measure a blood pressure in arms. So it usually, let's say take a normal person, 120/80, and the same person, you measure the blood pressure over the calf, it's 130/70. Systolic always will be on the higher side, diastolic will be a bit lower. So you measure the pulse pressure is 40 in arms, which is pulse pressure is systolic minus diastolic. 120 minus 80 is 40. Whereas in legs, 130 minus 70 will be 60. So both systolic is higher in the arms, and we look at it, systolic both here is higher. Systolic and pulse pressure both are higher in the legs compared to the arms. But blood still flow from your upper body to your lower body. Okay, even though it's also gravitational effect, I'm just giving example. Let's say took from proximal to distal side. As I said, distal arteries have a higher blood pressure. Why is it so? How blood flow against a pressure gradient? Because pressure is systolic and also pulse pressure all are higher, lower compared to the lower limb system. But how the blood can flow against pressure gradient? As I mentioned earlier, what we are interested in, what makes the blood flow in a system is the MAP, mean arterial pressure. Flow depends on mean arterial pressure. That's why NS, we're always interested in mean arterial pressure. We don't care much about systolic or diastolic. So you calculate your MAP. As we already learned that day, MAP is 1/3 pulse pressure plus diastolic blood pressure. I'll come to the derivation. How do we actually get this formula? Some people doesn't understand how do we get it. So I had a few slides on that as well. So you all can look at it again. So we calculate our MAP, 1/3 pulse pressure, 1/3 divide 40, which is 13.3, plus your diastolic blood pressure 80, you get 93.3 in upper system. Lower system, 1/3 pulse pressure, 1/3 of 60 is 20, plus 70 is 90. You see, MAP is still higher in the upper limb system compared to lower limb system. So this difference in pressure gradient is pushing the blood in the system. That maintains the flow. So MAP is important to maintain your systemic circulation, not your systolic blood pressure or pulse pressure. So again, this is another full example. When you talk about aorta, large arteries, arterioles, then it goes to capillaries and venules, large veins and vena cava. We talked about the compliance of your venule system. When they are highly compliant, they need pressure to maintain the volume. So they have lower pressure. When they have totally lower pressure, of course, the arterial system higher pressure, they can maintain the flow. The MAP difference you can see. This is about the systemic, when you talk about pulmonary venous circulation. You see, venous circulation pressures are all very low. So, of course, their mean arterial pressure will be much lower compared to the arterial system. That means pulsatility and the flow in the system. Systemic versus pulmonary circulation. Again, your mean arterial pressure in your pulmonary artery, pulmonary vein, or if you talk about your mean arterial pressure in a patient with under 20, your mean arterial pressure is 93.3. But whereas in your pulmonary circulation, your mean arterial pressure is only 14. So that's why the blood can push through from your right heart into the pulmonary circulation. Okay, then it can comes back. The blood, the flow is maintained by the mean arterial pressure. So if you talked about so much about mean arterial pressure, so, and we know mean arterial pressure is equivalent to cardiac output times systemic vascular resistance. That is the ultimate formula. So how do they come to this formula where mean arterial pressure is 1/3 pulse pressure plus diastolic blood pressure? How do they actually derive it? Why there is 1/3 here, everything? So I would like to go a bit more detail on that. So mean arterial pressure, as it said mean, it's an average BP during the cardiac cycle, which is average of blood pressure during systolic and diastolic blood pressure, because your cardiac cycle composed of your systolic and your diastolic phase. So it is the average BP during these two phases. But we use this formula instead of that. So MAP is equal to diastolic blood pressure plus 1/3 pulse pressure. How do we get it? So we know pulse pressure is systolic blood pressure minus diastolic blood pressure. And then finally, we come to this diastolic blood pressure plus 1/3 pulse pressure lah. That's how we do get it. So why there is 1/3? Why this thing is just a simple arithmetic calculation. It's a derivation. I'm just going to go very fast. So again, MAP is average during, so one complete sequence of ventricular systole and diastole. Okay, cardiac cycle means one complete sequence of ventricular systole and diastole. In a normal heart rate patient, it takes around 0.8 seconds. Okay, so you can see 1/3 is systole, 2/3 is diastole. I'm not going to go into detail about cardiac cycle. That's for another day. So 1/3 is your systole, 2/3 is your diastole. So what are the phases? Phases of systole, yeah, you have isomallometric contraction, isotonic contraction, protodiastole. Okay, these are the, it's only comprised of 0.27 second, which is 1/3 of 0.8 second. So 1/3 of cardiac cycle is your systole phase, and diastole, which comprise for 0.53 second, it gonna contribute to 2/3 of a cardiac cycle, which has 4 phases here. So that's why 1/3 of, when we talk about our BP, MAP again, MAP is equivalent to 1/3 systolic blood pressure plus 2/3 diastolic blood pressure. Because 1/3 of your cardiac cycle is contributed by systolic phase and 2/3 is contributed by a diastolic phase. MAP is the average of systolic and diastolic, where we take 1/3 systolic blood pressure plus 2/3 diastolic blood pressure. But from here, we derive to diastolic blood pressure plus 1/3 pulse pressure. How do we do it? So again, pulse pressure is equivalent to systolic blood pressure minus diastolic. You rearrange it. Systolic blood pressure is equivalent to pulse pressure plus diastolic. You move this here. You rearrange to get diastolic blood pressure. Diastolic blood pressure will be systolic blood pressure minus pulse pressure. Remember this, put into this equation now. 1/3 systolic blood pressure. This equation comes into here, plus 2/3. Open this up, 1/3 pulse pressure, 1/3 pulse pressure times 1/3 diastolic blood pressure, 1/3 times pulse pressure, 1/3 times diastolic blood pressure. So 1/3 pulse pressure plus 1/3 diastolic pressure plus 2/3 diastolic pressure. Sum this up, 1/3 plus 2/3 becomes 3/3, which is 1. So that's how we get 1/3 pulse pressure plus diastolic blood pressure. Okay, this is a simplified form of this whole lengthy equation. Okay, somebody did ask me how do we get this 1/3 the day. So this is just for explanation for that. Okay. So next we move on to the core of the topic today, volume, flow, and velocity. So how these three things is interrelated. So all this comes into a fluid dynamics. So when we talk about volume, it's the amount of a blood that occupies a vessel, okay, in the blood vessel, okay, that is the amount of a blood, let's say 5 ml, 10 mils, whatever, or we can measure in centimeter cube as well, okay, cubic centimeter as well. So what is flow? Flow is volume of the blood flowing through a vessel over a period of time. So you can see this is the blood that's flowing. It is flowing over this period of time. Let's say it take 1 second to reach from this point to this point. This length of the vessel, it takes this much time to reach this much of volume to reach from here to here. So that is flow. So what is velocity? Velocity is distance over the time. Okay, we have a volume of blood. How the same distance 1 second, within the 1 second, how much of the distance of the blood vessel it can cover? That is velocity. So velocity is distance over the time. The same blood volume within a stipulated time, how much length they can cover. Whereas flow is volume over the time. Within the stipulated time, how much volume they can cover. That is the flow. Okay. So remember these differences. Flow and velocity are not the same, but they are interrelated. Okay, they are interrelated. So again, we came to the main equation. Cardiac output equivalent to pressure gradient MAP divided by systemic vascular resistance, or flow equal to pressure gradient divided by resistance, any resistance, be it in the cardiovascular system, cerebrovascular system, renal, anything, doesn't matter. So it also goes back to the Ohm's law where pressure gradient is over resistance. You have two vessels, a normal blood vessel which is not vasoconstricted. It means resistance is lower. Okay, no vasoconstriction, resistance is lower. So resistance lower means your pressure, your flow will be higher. Okay, because low pressure thing. If you have a narrow blood vessel, higher resistance, your flow will be lower. If you're going to rearrange MAP equivalent to cardiac output times systemic vascular resistance, since your resistance is higher in systemic vascular in a patient who are vasoconstricted, of course your MAP will be higher. Okay, high pressure gradient, higher flow. Pressure gradient is directly equivalent to your flow. Okay, high pressure gradient, higher flow. If you have two venous system, where you're going to give a simple example of your blood, you are pushing blood into a patient. Okay, you just put in a bag of 1 pint of packed cell, you connected to a large bore cannula, is running. So the pressure difference, that's why we hang it higher than the patient, because there is a hydrostatic pressure, and that causes a hydrostatic pressure because of the difference in the height. That gonna cause a different pressure, the blood to flow through. But you want to make it go faster, the flow to be faster, you apply a pressure bag on top of your 1 pint of packed cell, and you increase the pressure. So now the pressure in the pint of packed cell is much higher than your arterial venous system. So the blood will flow faster. That is the simplest example. Higher resistance and lower flow. Okay, you inserted the granula. Now you're transfusing blood. But unfortunately, by mistaken, your staff nurse has put a BP cuff on the same end at the upper arm. So BP is cuffing now. So there is a resistance to the flow. The blood is going through a venous system, but there is a resistance to the flow. The vessels are being compressed. So that increases the resistance. So the flow will be lesser. That is the idea of it. So to maintain the same flow, let's say there is an increase in resistance or anything. So how do we maintain the same flow? Either we need to vasodilate. Means to maintain we have to manipulate the resistance. Either you vasodilate or vasoconstrict. So that's going to increase, or alter the radius of the vessel by vasodilating. How do we do this? By altering the radius of the vessel. When you vasodilate, you increase the radius of the vessel, the resistance will drop and the flow will increase. Okay, or we maintain a higher pressure gradient. That is why, as I mentioned, distal vessel need a higher systolic blood pressure. Okay, when you have a higher systolic blood pressure, your pulse pressure differences will be higher. That the pulsatility nature will maintain the flow, and also your MAP will be different. So this is again a repetition of it. Aorta to vena cava, the differences is, I'll just leave it here. Why there is systemic vascular resistance is much lower in the capillary system despite being very small because they are not going in parallel. They are not going in series. They are going in parallel system. When you branch out, the resistance will drop. A simple example, you're going on a road, there's only one road, one-way road, a lot of cars are going there. Of course, there'll be a lot of resistance. But there have been a bypass. They open up few more roads which goes into that. So a lot of people take a diversion. The car will go into multiple roads. The resistance drop. The same idea here. The amount of blood comes through here. It takes multiple pathways. So the resistance drop. So parallel resistance is much lesser than serial resistance. Our blood flows through in a parallel circulation. Okay. Next, we talk about the flow rate through a vessel. We are talking about so much of the flow and everything. So what are the determinant factor? We only talk about pressure now. The pressure gradient is the important factor to maintain a flow through a vessel and also the resistance. What are the other factors that also determines the flow through a vessel? So what we talk about here is same equation. Flow is equivalent to pressure gradient divided by resistance. Depends on pressure drop along the vessel and resistance to the flow. Very simple from the equation itself. Okay. So you see this is the cylindrical represent our vessel. The volume flow rate is equivalent to pressure gradient P1 minus P2, pressure here minus pressure here, the difference in pressure divided by resistance. So but the pressure drop is direct. We know this is this. But what determines the resistance? What are the things that determines the resistance? The resistance depends on these factors. The vessel diameter. The bigger the diameter of the vessel, it will come down. So the resistance formula is equal to 8NL divided by pi R4. 8NL divided by pi R4, which is equal to the R is the radius. Okay. When the radius is low, your resistance will be high. Okay, it's inversely proportional. Your low in radius means your smaller the vessel, increase in the resistance. Is to pi to R4 means is any increase in 1 meter resistance, it will increase by 16 times. I'll come to the calculation later lah. Okay, it's to the power of 4. Next, we go to L is the length. As long as the length of the tube is higher and longer, the resistance will be lower and lower. Okay, because the length of the vessel and fluid viscosity. Sorry, it's inversely directly proportional. The longer the length of the vessel, higher the resistance because the length of the vessel will produce friction to the blood flow. Higher friction. So that is a resistance to the blood flow and also the blood viscosity. Viscosity means the thicker or more viscous the fluid, the higher the resistance. Very easy, you are giving a crystalloid versus you are giving a blood. Of course, the fluid, the crystalloid or normal saline can go without much resistance because less viscous compared to your blood. So that is the difference between your viscosity and also the blood. Okay. Another example where the resistance higher is simple. You take a syringe of 5 cc and you take a syringe of 20 cc. When you want to inject a 20 cc syringe, you will have to apply more force because this goes back to our simplest equation where pressure is equivalent to force over area. Since the area is bigger, you have to apply more force to achieve the same pressure. Okay, that's how it goes back to that. Okay, so because when we rearrange, force is equivalent to pressure times area. The area is bigger, force have to be bigger to maintain the same pressure, to maintain the fluid to go in. Okay, so your resistance depends on your vessel diameter, which is inversely proportional, and vessel length and viscosity, which is directly proportional. So from this, we come to a equation which is again Poiseuille equation, which is interrelate all these things in one. Okay, which comes to it simply talks about fluid dynamics in laminar flow. This is very important. Again, Poiseuille law talks about laminar flow only. It only applicable in laminar flow. Okay, so what does this say? Flow, which is liters per second, is equivalent to pi is the constant, a pressure gradient times radius divided by 8NL. If you can see, flow is inversely proportional to resistance. So resistance equation is 8NL by pi R4. So for flow, it just reverse it. So the R4 will be on top and 8NL will be down. So to maintain a flow, you must have a higher pressure gradient. You have a higher pressure gradient, flow will be higher. You have a higher radius, vessel is big, or using a large bore cannula, you're using a bigger volume of system, you are using a bigger um, cannula, or you are using what I wanted to say, one is cannula, another one your ETT. If you're talking about your airflow, higher ETT, bigger ETT, you are given a more flow, easier to flow to go in. Divided by 8 NL, viscosity. Thicker the blood, lower the flow. Length, longer the length, lesser the flow. That's why we don't want to give a lot of ETT. If you're using an ETT or circuit, we don't want to have a lot of extension. Same goes to your drips and everything. You have a longer extension, the flow have a more resistance. Okay, this is this. So you have to know this. Again, Poiseuille law, it will be applied in multiple scenarios in your physiology. Talk about any system, this is involved. And even in your pharmacology, in some drug administration, everything, you have to know this as well. Okay. So this is just an extra information for those who might have problem when you're looking at few books. I just want to say this is the most commonly used formula where you use radius, so it will be 8 NL. In some books, you might find out 1 to 8 NL, and the pi equal to D4. The difference is this is diameter. When you use diameter, it will be 1 to 8. Whereas when you use radius, it will be 8 and 8 only. So D stands for diameter, radius. So what is how they are related? It's simple. Radius is just half of it. Diameter is the full length of it. Okay. So diameter, radius is 2 times diameter. Okay. Radius is 2 times diameter. So if you use diameter, the formula is different. When you use radius, which is the most commonly used formula, pi PR4 divided by 8 and L. Okay. You have to know this. So we talk about fluid dynamics in laminar flow, but all our flow are not laminar. Sometimes it's become turbulent. So how do we decide or determine when it is turbulent and when it is laminar? So that brings us to laminar versus turbulent. Laminar means it's a smooth flow. Laminar flows are smooth and streamlined. You can see like this. It has a central peak which has the highest velocity, and towards the edges, towards the vessel wall, the velocity comes down, and almost at the vessel wall, it is already very nil velocity or almost zero the velocity. Whereas in turbulent, it's a very irregular and chaotic flow. They don't have a streamline like this. They don't have go in a parallel situation. They go in a very irregular manner. So how do we decide? How do we know which is a laminar flow, which is a turbulent flow? That one more. What is the importance of laminar flow? We always want laminar flow. We don't want turbulent flow because of this, as I mentioned, the velocity of it, the importance of it, I'll come into a clinical application later. The linear velocity is very important, where the highest velocity in the center, where the lowest velocity at the edges or at the walls and everything. So that brings us to Reynolds number. Reynolds number is help us to determine the flow is likely to be laminar or turbulent. So this will tell us how we can manipulate. What should we do to maintain a laminar flow? So the equation is RE stands for Reynolds number. Reynolds number does not have a unit. So it come out in MTF and everything. Reynolds number does not have a unit. Okay. It equivalent to P in small, which is density, not pressure here. Okay. It's P is density, V is velocity, and D is diameter. Okay. Divided by mu, which is viscosity. Okay. Viscosity. Okay. So this is the different equation for Reynolds. Okay. Reynolds numbers PVD stands for density, velocity, and diameter divided by viscosity. So velocity is up, viscosity is down. Okay. So it's gonna tells you if the fluid is very dense, the RE gonna be higher. If the fluid is moving at a very high velocity, the Reynolds going to be higher. If the diameter of the pipe is bigger, it's going to cause high in Reynolds number. Or if the viscosity of the thing is high, then it's going to reduce the Reynolds number. So this is inversely proportional. So we look at it. So when you calculate, if you put in this and you get a number, If it's less than 2000, they say it's likely to be laminar flow. The number is 2000. And if it's more than 4000, there is likely to be turbulent flow. Anything in between, they call it a transitional flow, which is a mixed laminar versus plus turbulent. So the number to remember is 2000 and 4000 can come out in MCQ. Reynolds number does not have a unit. Okay, this all will cancel out the unit. Okay, you have to remember the upper part is density, velocity, and diameter, whereas down there is viscosity. I used to remember as DVD lah. Okay, density, velocity, and diameter, DVD over viscosity. Okay, so you all have to remember this. Okay, so you can see here Reynolds number is based on inertia forces or viscous forces. All these are inertia. The density, velocity, and diameter determine the inertia, the momentum of the fluid, whereas the viscosity is against the momentum, the viscous forces. So Reynolds number increased if velocity increased, charismatic dimension, okay, increase, density increase, but dimension means the diameter. Viscosity, it will reduce in viscosity, will increase the Reynolds number. Simple example, you giving your water versus your blood. Okay, when you give blood, it is highly viscous. So Reynolds number will be low, it will be laminar flow. Whereas if you give water, it will be very less, very diluted, less viscous, the Reynolds number will go high. So that's how we see it. So we come to the last section of it. Laminar versus turbulent flow. Why are we so important about the flow? Why do I talk so much about the flow, the laws and everything, the clinical importance of it? So you look at it. This is the, as I mentioned just now, we talk about, again, Poiseuille law talks about this, then we talk about Reynolds number. So again, Poiseuille law only for laminar flow, whereas Reynolds number is for your to determine laminar versus turbulent. So what are the importance? When we talk about again Poiseuille law, I'll give an example. I'm not gonna show in the slide. These are all day-to-day clinical application. You have a patient with anemia. So whenever you have a patient with anemia, you're gonna be viscosity. Your blood is thin. Okay, it's more diluted. Your diluted. Hematocrit gonna be lower. So your viscosity is reduced. So when your viscosity is reduced, your flow will be faster. So if you come in again here, when your viscosity is reduced, your Reynolds number going to be higher. So it's going to end up in turbulent flow. So turbulent flow, we go back here, turbulent flow. It's not good because why is it laminar flow is important? If you look at it, we want your blood vessels are here. This is your wall of your blood vessels. So your cells will be here. All your cells will be here. So your oxygen, your RBC gonna carry your oxygen and everything. At the edge of the vessel, they're gonna do gas exchange. There'll be an exchange of gases, carbon dioxide coming in, oxygen goes out to the cell, or exchange of nutrient products and everything. Your RBC needs certain amount of time to be sent in this smooth flow for the gas exchange all occurs at the optimal level. If the flow is turbulent like this, then it won't have a smooth flow or smooth gas exchange or gas exchange of nutrient products and everything, waste and everything. So for an optimal gas exchange or optimal any exchange to occur over a vessel wall to the cellular system, we need to have a laminar flow. That's why if the patient is anemic, it's gonna be a turbulent flow and these all gonna be interrupted. That's why ideally, classically, you see in IHD patient, ischemic heart disease patient, we will always say keep the hematocrit at 10 and above, 10 and above. Because if you keep lower, the patient already hypoxic, ischemic and everything. Then the patient gonna have a turbulent flow. The gases exchange gonna be very bad. Patient gonna get even more ischemia. So why is it 10? We know hematocrit is HB times 10, 30. 30 is the optimal hematocrit to maintain the laminar flow according to many studies. But this is all has been debunked and everything. But we just gonna go traditional. We're not gonna go dwell into much. We're just gonna take it traditionally. Okay, so that is the importance of maintaining a certain hematocrit. So if it's very good to maintain very slow flow, why don't we maintain hematocrit of 40? Because if you maintain 40, so increase in viscosity, you're gonna reduce the flow, very slow flow. Very slow flow gonna make blood stasis. They're gonna end up in thrombus. You're gonna get DVT, you're gonna get thrombus, which is not good as well. So the because as I said, the blood flow at the wall is almost zero. if you're going to increase the hematocrit, the blood flow going to be even lower. Even here, all the velocity will be come down. So velocity comes down, the blood going to stasis in the vessel for so long, that's going to end up in thrombus. Okay, we are increasing the thrombogenic property in the vessel. That's why we don't do that. Another idea of patient having atherosclerosis. When they have atherosclerosis, the diameter of this vessel is reduced. So diameter high, you get increase in Reynolds number. But when the diameter is reduced, but the Reynolds number will still go high because this is related to the area. That is even more depth. That is the one contradicting thing you have to know, because you have to incorporate velocity. You have to put in an area formula here. So I'm not going to go into it, but just remember, atherosclerosis, there is something impeding a laminar flow. There is a plaque. So the Reynolds number will also go high there. Another example, as I said, in RS system, helium. In upper airway obstruction, we will give helium to the patient. Because why? Helium is a lower density. When you talk about this resistance, we go to this resistance formula. Just now we talk about resistance formula. Resistance is 8 NL over pi R4. When a patient comes with upper airway obstruction, it means very high resistance are present. So we use helium. Helium is a very low density gas. So helium will bring down the resistance. Okay, low density, low resistance to the airflow. So it also used in not only fluid, it's also in airflow in RS system as well. That's another example. And other example as I give you is large bore branula. All this comes into play here lah. Okay, we talk about this. When you use a large bore branula, the diameter is much increased, the flow is higher. You don't use a very lengthy system, okay, short length, so the flow will be better as well. Use a pressure bag, so pressure gradient is increased. You warm the blood. Why don't you give a cold blood? You warm the blood because warm blood are less viscous. Cold blood are more viscous. They're going to reduce the flow. So all these are examples how we can come to it. At the end, last two slides about LaPlace Law, because they are very interrelated. LaPlace Law talks about wall tension of a holosphere or cylinder is proportional to both the pressure of its content, its radius. So they all talk about this pressure, radius and everything, you know, they are very interrelated. So it is applied for cylindrical or hollow spherical vessel. Cylindrical is your vessel wall. Spherical will be your heart, your myocardium, your left ventricle, your chambers. So the equation is wall tension is equivalent to pressure times the radius. Okay, pressure of the content from radius. Whatever the content, they will internal pressure, they will liberate internal pressure. So the tension is equivalent to the radius of the cylindrical vessel times the pressure that is being liberated by the content. If it's a spherical like a chamber, the equation will be PR divided by 2. Okay, that is the difference between cylindrical and your radius. So how do we calculate pressure from here? T is PR. If you want to calculate the pressure gradient, you just rearrange. So the pressure gradient will be equivalent to tension divided by resistance. This is for cylindrical. For spherical organ like chamber or your heart chamber, it will be 2T over R. So what is the clinical important? Again, we talk about auto-regulation. When we have auto-regulation, especially in your cerebral blood flow, you are maintaining a certain blood pressure. You within 50 to 150 millimeter mercury, the cerebral blood flow is maintained because the pressure is maintained. How the pressure is maintained? Because the tension of the wall is maintained because the vessel will dilate and the blood pressure is keep increasing 50 to 100 millimeter mercury. If you look at it, if the pressure increase, the wall tension must increase, but the vessel will vasodilate to reduce the to vasoconstrict to reduce the radius, to reduce the retention. The auto regulation is mainly based on your LaPlace law, especially your cerebral blood flow. I don't have cerebral blood flow graph here. You all can go read about it. Another important factor where we use LaPlace law is on your alveoli, your surfactant. How does the surfactant reduces your tension, the alveoli tension? Also based on your LaPlace law. Another thing is your ETT. How does your increase in your ETT size and reduces the resistance and everything all comes into play here. Okay. So then another one we talk about your LaPlace law is your bruit. If you have your carotid stenosis, you can palpate, you'll feel a bruit, because when you have a carotid stenosis, the stenosis gonna reduces the pressure. So it gonna reduces the radius. So when the radius reduce, your pressure will be very high. That's why you feel the bruit, because the tension is increased. So that's why the pressure is feel. There are a lot of clinical applications like this. But what I want to remember for you to remember is these equations and this equation. This is applied in the vessel wall. This is applied in your myocardium. Myocardium, another example is your left ventricular hypertrophy. If you have a left ventricular hypertrophy, your internal radius of your left ventricle internal cavity is reduced. When your cavity is reduced, your pressure goes high. When your left ventricle hypertrophy, the myocardium undergoes an increase in tension. So increase in tension also causes increase in pressure. That's why patient with cardiomyopathy, they have systemic hypertension, because if you look at it, pressure is equivalent to 2T over R. They will have left ventricle hypertrophy. The left ventricle hypertrophy causes increase in tension in the myocardial wall. So directly increases the pressure. And the radius, the ventricular cavity, because the myocardial wall has been thickened, the lumen becomes smaller. So the radius becomes smaller, also increases the blood pressure. So that's all for I think next week I will cover about RS, enough about